Hello, welcome back to my channel, and in this video we are going to do more problems on quantum mechanics. And in this question we have this particle with mass m, and which has this wave function where a, the big A and the small a are positive real constant, and you need to find this big A, the normalizing factor, and for what potential energy. This is a solution to Schrödinger equation. You already given the wave function, you need to find out what potential energy this corresponds to, and then we're gonna calculate the expectation values of x square, p, and p square, and then we're gonna find our standard deviation in x and standard deviation in p, and then we're gonna take a product of that and see it matches with consistent with the uncertainty principle. So this is a very typical kind of question for quantum mechanics. Initial beginning when you're doing some basics, this is something you should know how to do that. So let's go and do it. Okay, so the first thing we need to find A, and this we have done this so many times, but in this case you're given a wave function, so you need to square the wave function. If you're given a probability density function, you can do it as it is, but if you're giving a wave function, you need to square the wave function. And this case our function are when you square the wave function, the imaginary part cancels out and you'll just left with this real part, and the real part is even. And so if it's even, you can, instead of doing integration from minus infinity to plus infinity, you can multiply with 2 and do integration from 0 to infinity, and this is should be equal to 1. This is what we learned, the normalizing condition, and from that you can find A. And these are those Gaussian integrals, and these you can find online. I'm not gonna calculate how to. I'm not gonna tell you how to do it. You can just find it online. Even when you're doing exam, this should be given to you. It's more about the process and how you tackle the problem rather than all the mathematical things you can remember. After you find all that, all the integration and all, you can simplify this to find A, and you will find A to be this 2am divided by pi to Planck constant to the power 1/4. So this is our normalizing factor. Now what we need to do, we need to find what potential energy, we already given a solution, and we need to find what potential energy this correspond to in the Schrödinger equation. So now you're given the wave function, you can take the derivative with respect to t. You get this minus ia times wave function, and then you can also do this derivative with respect to x. You get this minus 2amx divided by h multiply with psi. And basically what you're doing is you're going to calculate all this and you're going to plug that into Schrödinger equation, and then you can figure out what will be the potential energy. That is the strategy. And then Schrödinger equation has a second derivative with respect to x, and you do that and you get this expression where you have minus 2a multiplied with m divided by Planck constant whole multiplied with minus 1 minus 2a m x squared divided by h times this wave function, and you get this expression. And now what you're gonna do, you have the Schrödinger equation, you can plug that all in, and you have this psi derivative of this side with respect to t, and you have double derivative with respect to x. So you can plug that in Schrödinger equation, and then you can match is the potential energy, because anything you get with anything that has a factor of this psi, anything with the factor psi, that will be your potential. And once you simplify all those things, you will find out you can you get this factor of psi, and you simplify this, you get this as a factor of this psi, and the factor of the factor that is in front of the psi would be your potential energy. So now what we're gonna do, calculate this expectation value of x square, p, and p square. This is very common in this case. Now this is a odd integral. If you calculate the expectation value of x, you will find out this is an odd integral, and that becomes 0. But when you're doing with respect expectation value of x square, you have this Gaussian integral, and you multiply with x square, and you have already available, you will find online this generalized answer of the Gaussian integral, and you can use those. And as I always said, this should be provided to you even when you're doing an exam. So after doing all the integration and simplifying this, you get this expectation value of x squared to be Planck constant divided by 4am. And then similar to p, because p is the derivative with respect to the expectation value of x. Expectation value of x is 0, so expectation value of p is 0. Now you're gonna do with respect to p square, and this is much more involved. We know how to calculate the p square. We know what is p, right? It's minus h um, multiplied with the d over dx, and now we're gonna square it, and you get this expression. And now you have this expression, you can simplify it, and you get you can simplify it, and you can do integral, because this is a integration with respect to x square, and that should be easy. And go through it, look at it, and this is actually quite easy. What you're gonna figure out that is that this is gonna become the only integral part is this x square, and you have this psi and this psi, and this gonna become the expectation value of this x square, which we already calculated before, and that you're gonna plug it in, and you're gonna get a simplified expression for this p square. Yeah, so this is how you need to do. I already done this for you, and you can do it on your own and see if matches with what I've shown. And then you have this and yeah, so this can simplify to this am Planck constant. Yeah, now what we're gonna see, now what we're gonna do is we're gonna calculate the standard deviation of x and p, and gonna see it consistent with the uncertainty principle. So we have seen this definition a lot of time, where you have this this variance x square, expectation value of x square minus the square of this expectation value of x, and we all got all the expression, and you're gonna just plug it in, and you're gonna see you're gonna get all this expression. And similar to p, you're gonna get this square root of amh square, and you're gonna multiply those things, and you're gonna see this is matches exactly h pi over 2. This is a very special problem because it exactly matches h by 2, but that need not to be the case. For this product to be consistent, it just need to be greater than or is equal to this Planck constant divided by 2. I hope you like this video. If you do, give the thumbs up, and I will see you next time. Like, share, and subscribe.